Hi, I'm Seema, and I work on Swift and Swift UI. In this video, you will learn how to elevate your app with Swift concurrency. As app developers, most of the code we write is on the main thread. Single-threaded code is easy to understand and maintain. But at the same time, a modern app often needs to perform time-consuming tasks, like a network request or an expensive computation. In such cases, it is a great practice to move work off the main thread to keep the app responsive. Swift gives you all the tools you need to write concurrent code with confidence. In this session, I will show you how by building an app with you. We'll start with a single-threaded app and gradually introduce asynchronous code as we need to. Then, we'll improve the performance of the app by offloading some of the expensive tasks and running them in parallel. Next, we'll discuss some common data race safety scenarios you might encounter and explore ways to approach them. And finally, I will touch on structured concurrency and show you how to use tools such as a task group for more control over your concurrent code. I can't wait to get started. I love journaling and decorating my entries with stickers, so I will walk you through building an app for composing sticker packs out of any set of photos. Our app will have two main views. The first view will feature a carousel with all stickers with a gradient reflecting the colors from the original photo. And the second one will show a grid preview of the entire sticker pack, ready to be exported. Feel free to download the sample app below to follow along. When I created the project, Xcode enabled a few features that provide a more approachable path to introducing concurrency, including main actor by default mode, and a few upcoming features. These features are enabled by default in new app projects in Xcode 26. In the Approachable concurrency configuration, the Swift 6 language mode will provide data race safety without introducing concurrency until you are ready. If you want to enable these features in existing projects, you can learn how in the Swift migration guide. In code, the app will have two main views: sticker carousel and sticker grid. These views will use the stickers that the photo processor struct is responsible for extracting. The photo processor gets the raw image from the photo library before it returns the sticker. The sticker grid view has a share link, which it can use for sharing the stickers. The photo processor type performs two expensive operations: the sticker extraction and the dominant colors computation. Let's see how Swift concurrency features can help us optimize for a smooth user experience while still letting the device perform these expensive tasks. I'm going to start with the sticker carousel view. This view displays the stickers in a horizontal scroll view. Inside of the scroll view, it has a for each, which iterates over the array of selected photos from the photo library stored in the view model. It checks the processed photos dictionary in the view model to get the processed photo corresponding to the selection in the photo library. Currently, we don't have any processed photos since I haven't actually written any code to get an image from the photo picker. If I run the app now, all we will see in the scroll view is the sticker placeholder view. I'll navigate to sticker view model using command click. The sticker view model stores an array of currently selected photos from the photo library, represented as a selected photo type. I'll open Quick Help with Option Click to learn more about this type. Selected photo is an identifiable type that stores a Photos Picker item from the Photos UI framework and its associated ID. The model also has a dictionary called Processed Photos that maps the ID of the selected photo to the Swift UI image it represents. I've already started working on the load photo function that takes the selected photo. But currently, it does not load any data from the photo picker item that it stores. The photos picker item conforms to the transferable protocol from the SDK, which allows me to load the representation I request with the asynchronous load transferable function. I will request the data representation. Now we have a compiler error. It's because the call to load transferable is asynchronous, and my load photo function where I call it is not set up to handle asynchronous calls. So Swift helps me by suggesting to mark load photo with the async keyword. I'm going to apply this suggestion. Our function is capable of handling asynchronous code, but there's still one more error. While load photo can handle asynchronous calls, we need to tell it what to wait for. To do this, I need to mark the call to load transferable with the await keyword. I'll apply the suggested fix. I'll call this function in the sticker carousel view. With Command-Shift-O, I can use Xcode's Open Quickly to navigate back to the sticker carousel. I would like to call the load photo function when the sticker placeholder view appears. Because this function is asynchronous, I will use the SwiftUI task modifier to kick off photo processing when this view appears. Let's check this out on my device. Great, it's up and running. Let's try selecting a few photos to test it out. Great. Looks like the images are getting loaded from my photo library. The task allows me to keep the app's UI responsive while the image is being loaded from the data. And because I'm using lazy HTAG for displaying the images, I'm only kicking off photo loading tasks for views that need to be rendered on screen. So the app is not performing more work than necessary. Let's talk about why async await improves responsiveness of our app. We added the await keyword when calling the load transferable method, and annotated the load photo function with async. The await keyword marks a possible suspension point. It means that initially, the load photo function starts on the main thread, and when it calls load transferable at the await, it suspends while it's waiting for load transferable to complete. While load photo is suspended, the transferable framework will run load transferable on the background thread. When load transferable is done, load photo will resume its execution on the main thread and update the image. The main thread is free to respond to UI events and run other tasks while the load photo is suspended. The await keyword indicates a point in your code where other work can happen while your function is suspended. And just like that, we are done with loading the images from the photo library. Along the way, we learned what asynchronous code means, how to write, and think about it. Now, let's add some code to our app that would extract the sticker from the photo and its primary colors that we can use for the background gradient when displayed in a carousel view. I'm going to use Command-Click to navigate back to Load Photo, where I can apply these effects. The project already includes a photo processor, which takes the data, extracts the colors and the sticker, and returns the processed photo. Rather than providing the basic image from the data, I'm going to use the photo processor instead. The photo processor returns a processed photo, so I'll update the dictionary's type. This processed photo will provide us the sticker extracted from the photo and the array of colors to compose the gradient from. I've already included a gradient sticker view in the project that takes a processed photo. I am going to use Open Quickly to navigate to it. This view shows a sticker stored in the processed photo on top of a linear gradient in a Z-stack. I'm going to add this gradient sticker in the carousel. Currently, in the sticker carousel, we are just resizing the photo. But now that we have a processed photo, we can use the gradient sticker here instead. Let's build and run the app to see our stickers. It's working! Oh no, while the stickers are being extracted, scrolling through the carousel isn't that smooth. I suspect the image processing is very expensive. I have profiled the app using instruments to confirm that. The trace shows that our app has severe hangs. If I zoom in on it and look at the heaviest stack trace, I can see the photo processor blocking the main thread with the expensive processing tasks for more than 10 seconds. If you want to learn more about analyzing hangs in your app, check out our session Analyze Hangs with Instruments. Now, let's talk more about the work our app is doing on the main thread. The implementation of load transferable handled offloading the work to the background to avoid causing the loading work to happen on the main thread. Now that we've added the image processing code, which is running on the main thread and takes a long time to complete, the main thread is unable to receive any UI updates, like responding to scrolling gestures, leading to poor user experience in my app. Previously, we adopted an asynchronous API from the SDK, which offloaded the work on our behalf. Now we need to run our own code in parallel to fix the hang. We can move some of the image transformations into the background. Transforming the image is composed of these three operations. Getting the raw image and updating the image have to interact with the UI, so we can't move this work to the background. But we can offload the image processing. This will ensure the main thread is free to respond to other events while the expensive image processing work is happening. Let's look at the photo processor struct to understand how we can do this. Because my app is in the main actor by default mode, the photo processor is tied to the main actor, meaning all of its methods must run on the main actor. The process method calls extract sticker and extract colors methods, so I need to mark all methods of this type as capable of running off the main actor. To do this, I can mark the whole photo processor type with non-isolated. This is a new feature introduced in Swift 6.1. When the type is marked with non-isolated, all of its properties and methods are automatically non-isolated. Now that the photo processor is not tied to the main actor, we can apply the new addConcurrent attribute to the process function and mark it with async. This will tell Swift to always switch to a background thread when running this method. I'll use Open Quickly to navigate back to the photo processor. First, I'm going to apply non-isolated on the type to decouple the photo processor from the main actor and allow its methods to be called from concurrent code. Now that photo processor is non-isolated, to make sure that the process method will get called from the background thread, I will apply addConcurrent and async. Now, I'll navigate back to the sticker view model with Open Quickly. Here, in the load photo method, I need to get off the main thread by calling the process method with the await keyword, which Swift already suggests. I'm going to apply this suggestion. Let's build and run our app to see if moving this work off the main actor helped with the hangs. Looks like there are no more hangs on scroll. But even though I can interact with the UI, the image is taking a while to appear in the UI while I'm scrolling. Keeping an app responsive isn't the only factor for improving user experience. If we move work off the main thread, but it takes a long time to get results to the user, that can still lead to a frustrating experience using the app. We moved the image processing operation to a background thread, but it still takes a lot of time to complete. Let's see how we can optimize this operation with concurrency to have it complete faster. Processing the image requires extraction of stickers and the dominant colors, but these operations are independent of each other. So we can run these tasks in parallel with each other using async-let. Now, the concurrent thread pool, which manages all of the background threads, will schedule these two tasks to start on two different background threads at once. This allows me to take advantage of multiple cores on my phone. I'll command-click on the process method to adopt async-let. By holding down Ctrl-Shift and the down arrow key, I can use multi-line cursor to add async in front of sticker and colors variables. Now that we've made these two calls run in parallel, we need to await on their results to resume our process function. Let's fix all of these issues using the editor menu. But there's still one more error. This time, it's about a data race. Let's take some time to understand this error. This error means that my photo processor type is not safe to share between concurrent tasks. To understand why, let's look at its stored properties. The only property the photo processor stores is an instance of color extractor needed to extract the colors from the photo. The color extractor class computes the dominant colors that appear in the image. This computation operates on low-level, mutable image data, including pixel buffers, so the color extractor type is not safe to access concurrently. Right now, all color extraction operations share the same instance of the color extractor. This leads to concurrent access to the same memory. This is called a data race, which can lead to runtime bugs like crashes and unpredictable behavior. The Swift 6 language mode will identify these at compile time, which defines away the set of bugs when you are writing code that runs in parallel. This moves what would have been a tricky runtime bug into a compiler error that you can address right away. If you click the Help button on the error message, you can learn more about this error on the Swift website. There are multiple options you can consider when trying to solve a data race. Choosing one depends on how your code uses the shared data. First, ask yourself, does this mutable state need to be shared between concurrent code? In many cases, you can simply avoid sharing it. However, there are cases where the state needs to be shared by such code. If that is the case, consider extracting what you need to share to a value type that is safe to send. Only if any of these solutions aren't applicable to your situation, consider isolating the state to an actor, such as the main actor. Let's see if the first solution would work for our case. While we could refactor this type to work differently to handle multiple concurrent operations. Instead, we can move the color extractor to a local variable in the extract colors function, so that each photo being processed has its own instance of the color extractor. This is the correct code change, because the color extractor is intended to work on one photo at a time. So we want a separate instance of it for each color extraction task. With this change, nothing outside of the extract colors function can access the color extractor, which prevents the data race. To make this change, let's move the color extractor property to the extract colors function. Great! With the compiler's help, we've been able to detect and eliminate a data race in our app. Now, let's run it. I can feel the app running faster. If I collect a profiler trace in instruments and open it, I no longer see the hangs. Let's quickly recap the optimizations we made with Swift concurrency. By adopting the addConcurrent attribute, we've successfully moved our image processing code off the main thread. We've also parallelized its operations, sticker and color extraction with each other using async-let, making our app much more performant. The optimizations you make with Swift concurrency should always be based on data from analysis tools, such as the time profiler instrument. If you can make your code more efficient without introducing concurrency, you should always do that first. The app feels snappy now. Let's take a break from image processing and add something fun. Let's add a visual effect for our process stickers that will make the sticker scrolled past fade away and blur. Let's switch to Xcode to write that. I'll go back to the sticker carousel using the Xcode project navigator. Now, I'm going to apply the visual effect on each image in the scroll view using the visual effect modifier. Here, I'm applying some effects to the view. I want to change the offset, the blur, and opacity only for the last sticker in the scroll view. So I need to access the view model's selection property to check if the visual effect is applied to the last sticker. Looks like there's a compiler error because I'm trying to access main actor protected view state from the visual effect closure. Because computing a visual effect is an expensive computation, SwiftUI offloads it off the main thread for maximizing performance of my app. If you feel adventurous and want to learn more, check out our session, Explore Concurrency in SwiftUI. That's what this error is telling me. This closure will be evaluated later on the background. Let's confirm this by looking at the definition of the visual effect, which I'll click on. In the definition, this closure is sendable, which is an indication from SwiftUI that this closure will be evaluated on the background. In this case, SwiftUI calls visual effect again whenever selection changes, so I can make a copy of it using the closure's capture list. Now, when SwiftUI calls this closure, it will operate on a copy of selection value, making this operation data race free. Let's check out our visual effect. It's looking great, and I can see how the previous image blurs and fades out as I'm scrolling. In both of these data race scenarios we've encountered, the solution was to not share data that can be mutated from concurrent code. The key difference was that in the first example, I introduced a data race myself by running some of the code in parallel. In the second example, though, I used a SwiftUI API that offloads work to the background thread on my behalf. If you must share mutable state, there are other ways to protect it. Sendable value types prevent the type from being able to be shared by concurrent code. For example, extract sticker and extract colors methods are running in parallel and both take the same image as data. But there is no data race condition in this case because data is a sendable value type. Data also implements copy on write, so it's only copied if it's mutated. If you can't use a value type, you can consider isolating your state to the main actor. Luckily, the main actor by default mode already does that for you. For example, our model is a class, and we can access it from a concurrent task. Because the model is implicitly marked with the main actor, it is safe to reference from concurrent code. The code will have to switch to the main actor to access the state. In this case, the class is protected by the main actor. But the same applies to other actors that you might have in your code. Our app is looking great so far, but it still doesn't feel complete. To be able to export the stickers, let's add a sticker grid view that kicks off a photo processing task for each photo that hasn't been processed yet, and displays all of the stickers at once. It will also have a share button that would allow for export of these stickers. Let's jump back to the code. First, I'll use Command-click to navigate to the sticker view model. I'm going to add another method to our model, process all photos. Here, I want to iterate over all processed photos saved so far in my model. And if there are still unprocessed photos, I want to start multiple parallel tasks to kick off processing for them at once. We've used async before, but that only worked because we knew that there's only two tasks to kick off, the sticker and color extraction. Now we need to create a new task for all raw photos in the array, and there can be any amount of these processing tasks. APIs like Task Group allow you to take more control over the asynchronous work your app needs to perform. Task groups provide fine-grained control over child tasks and their results. The task group allows to kick off any number of child tasks, which can be run in parallel. Each child task can take arbitrary amounts of time to finish, so they might be done in a different order. In our case, the processed photos will be saved into a dictionary, so the order doesn't matter. Task group conforms to async sequence, so we can iterate over the results as they are done to store them into the dictionary. And finally, we're gonna wait on the whole group to finish the child tasks. Let's go back to the code to adopt a task group. To adopt the task group, I'll start by declaring it. Here, inside of the closure, I have a reference to the group, which I can add image processing tasks to. I'm going to iterate over the selection saved in the model. If this photo has been processed, then I don't need to create a task for it. I'll start a new task of loading the data and processing the photo. Because the group is an async sequence, I can iterate over it to save the processed photo into the processed photos dictionary once it's ready. That's it. Now we are ready to display our stickers in the sticker grid. I'll use Open Quickly to navigate to the sticker grid. Here, I have a state property, finished loading, which indicates if all photos have finished processing. If the photos haven't been processed yet, a progress view will be displayed. I'm going to call the process all photos method we just implemented. After all photos are processed, we can set the state variable. And finally, I will add the share link in the toolbar to share the stickers. I'm populating the share link items with a sticker for each selected photo. Let's run the app. I will tap on the sticker grid button. Thanks to the task group, the preview grid starts processing all photos at once, and when they are ready, I can instantly see all of the stickers. Finally, using the Share button in the toolbar, I can export all of the stickers as files that I can save. In our app, the stickers will be collected in the order they are done processing. But you can also keep track of the order, and the task group has many more capabilities. To learn more, check out the session Beyond the Basics of Structured Concurrency. Congrats! The app is done, and now I can save my stickers. We've added new features to an app, discovered when they had an impact on the UI, and used concurrency as much as we needed to improve responsiveness and performance. We also learned about structured concurrency and how to prevent data races. If you didn't follow along, you can still download the final version of the app and make some stickers out of your own photos. To familiarize yourself with new Swift concurrency features and techniques mentioned in this talk, try to optimize or tweak the app further. Finally, see if you could bring these techniques to your app. Remember to profile it first. To dive deeper into understanding the concepts in Swift's concurrency model, check out our session Embracing Swift Concurrency. For migrating your existing project to adopt new approachable concurrency features, check out the Swift Migration Guide. And my favorite part, I got some stickers for my notebook. Thanks for watching!